Howdy, chemistry. How you doing? Let's get ready for another flipped lecture. We're moving into a new kind of conversation today. We're looking at solutions. So we've talked about states of matter, and now we're going to look at what happens when one state of matter dissolves another state of matter, and we're going to talk about solutions today. So this is also kind of review. We did talk about this a little bit in physical science, but not to the detail that we're going to be discussing it today. So here we go. Moving on to solutions. So a solution is a mixture, which means it's not a compound, right? The different things that are in the container together are not chemically bound to each other. They're just sitting next door to each other. They're a mixture of a variable composition in one phase. That's going to become important. By one phase, we mean when you look at it, you see one thing. You don't see chunkiness and you don't see layers, right? A solution is homogeneous. So when we talk about different kinds of mixtures, there's homogeneous and heterogeneous mixtures. A solution is by definition a homogeneous mixture. And there are some vocabulary words we need to know here. The majority component, the thing that is doing the dissolving, is called the solvent. Now a solvent, we immediately think of a liquid, but they don't all have to be liquids. As you'll see in a minute, there are such things as solids that are solvents. But generally speaking, most of the time, the common solvent is a liquid, something that is dissolving something else. The minority component, the thing that is being dissolved, is the solute. So the solute is something inside the solvent. So we'll give you lots of examples here in a moment. Here we have just a picture. Solvent, the thing doing the dissolving. Solute, the thing that is dissolved. In this particular example, the solvent is a liquid and the solute is a solid. Most of the time, that's the way it is. Of course, there are exceptions, some of them very notable, but the stereotypical picture of a solution is you've got some powder and you pour it in some liquid and you stir it, right? And you get a solution. When you stand back and look at this, right now it's blue with yellow dots, but in truth, you would look right through and it would be a clear all-in-one phase kind of thing. No chunkiness, no layering, like the image I've got sitting up here, right? Okay. Some other examples of solutions. Here we have Kool-Aid waiting to be drunk, and we got the water hot and we poured the powder in and stirred it up. That's a solution, and it's all in one phase. This is not a solution. This is water and oil, and it looks like something else underneath it too. And because we see multiple layers, this is not one phase. This is three phases, so this would not be a solution. This would be a heterogeneous mixture, okay? Not a solution. This is a solution because it's all in one phase. You see one thing, okay? If you take, again, a solute, in this case, this is cobalt chloride, and you mix it with water, and you get this solution. Here we have the solid in the liquid, and it all goes into one phase. You don't see chunkiness or layers. This is a solution. Okay. Now, we can have different states of matter in a solution. It's not always a liquid dissolving a solid. Liquid solvents can dissolve other liquids or solids or gases even. So liquids which can form a solution with other liquids are said to be miscible. Miscible means they mix and they dissolve each other. And so the larger volume one would be the solvent, and the liquid that gets poured in and gets dissolved by the larger one would be the solute. If they separate, like the oil and water in the picture a second ago, then we would say that that is immiscible. It is unable to be dissolved, right? Picture of a solution. This is a liquid, water, that is in this case dissolving some sugar, which is a solid, and it's also dissolving some gas, which is carbon dioxide here, the carbonated beverage. So a soda is an example of a solution. It's actually multiple kinds of solute in one solvent. Water and then lots of stuff in it. Okay? This is not a solution. Again, this is a heterogeneous mixture of liquids because it's immiscible. The oil and the water do not mix. A solid solvent does exist. A solid can dissolve both liquids and solids and gases. You can have a solid dissolved in a solid, and I'll show you that in a minute. You can have liquids dissolved in a solid, and you can even have gases dissolved in a solid. So solids can be solvents. Gases can also be solvents, but if you have a gaseous solvent, you can only have gaseous solutes. So solids cannot be dissolved by a gas. They can be suspended in a gas, and we'll get to that later. But as far as solutions go, we can only have gaseous solutes in a gaseous solvent. Okay, so more pictures. Here we go. This is concrete. Concrete is a solid, and it is dissolving other kinds of solids. And so we have a solid solution here in concrete. This is brass and steel. Both of these are solids, metals, that are dissolved in other solids. So we have a mixture of different kinds of solids here. These are solutions of solids. This cloud, this is water dissolved in air. And so this is an example of a liquid dissolved in the air, and that's an example of a solution as well. Solvation. Now, not salvation. We at Calvary Chapel Christian School are big fans of salvation, different from solvation. Solvation is the process in which a solid solute moves into a liquid solvent. So it's how you make a solution, the process of becoming a solution. So the first step is dissociation. The solute has to separate into smaller bits, little bits, because it's hard to dissolve a crystal of salt, but it's really easy to dissolve salt powder. And so the smaller the pieces are, the easier it is to go into solution. And so the first step is dissociation. The solute has to dissociate and dissolve and go into as small a piece as possible. And then ionization, the solute particles ionize in solution, at least the ones that are being dissolved in a polar solvent. Sometimes this doesn't happen if you're dissolving in a non-polar solvent, but most of the time it does. So the solute separates into little tiny bits, and then those little bits become ions. They give and take electrons with the solution, and then they become ions, and then they integrate themselves into the solution. So here's a picture again. This is salt crystals. Here's water molecules. The salt breaks down into small bits, and the ions are surrounded by water molecules. So a positive sodium ion is going to be surrounded by the negative parts of the water molecule, and a negative chlorine ion is going to be surrounded by the positive parts of a water molecule, and that's how we make a solution. That's the process of solvation. Generally speaking, solvation is exothermic. Most of the time it releases more energy than it absorbs. It takes some energy to dissociate, and it takes even a little bit of energy to ionize, but the actual insertion of the solute into the solvent is a more stable setting than the other possible condition, and so it releases energy. Oftentimes making a solution, it warms up, and that's thermal energy being given off because it's a more stable form, and it's releasing energy in the form of heat. The amount of energy that is given off is called the enthalpy of solution. That's how much energy it's given off. And if you're going to take a solution and purify it back to a pure solute and a pure solvent, you're going to have to put that energy back into it. Okay, so the energy of enthalpy, or the enthalpy of solution, is going to be the energy that you get out by making a solution. Typically, like dissolves like. If you have a polar solute, you need a polar solvent. If you have a non-polar solute, you need a non-polar solvent. That's why oil and water don't mix, because they are not similarly polar or non-polar. Okay, this is just an energy diagram to show you that if we have pure components, we have to separate the molecules. That's dissociation. We have to separate the solute molecules as well and get them further apart. That takes energy. And then when they mix, most of the time it follows the red line, and it's an exothermic process where we have a change in energy that is greater than zero, and some energy is given off. Not all the time. Sometimes it breaks even. Sometimes it doesn't go all the way back down. These are the solutions you have to heat to dissolve. But most of the time you do get energy back. Okay, and again, like dissolves like, polar dissolves polar, and so that's what makes this joke funny. Help, help, I'm dissolving, says the polar bear. The grizzly bear says, but bears are insoluble. And it says, that's easy for you to say, you're not polar. Ha! Polar bear, get it? Water's polar. Okay, anyway. Solutes tend to dissolve faster at higher temperatures and pressure, which is why heating up water before you dump sugar into it lets you make syrup faster. And under greater pressure, that would be even easier, but most of us don't use a pressure cooker to make syrup because that's kind of weird, but it would work faster. So higher pressure, higher temperature, solutions are made quicker. Now, we have to define terms when we talk about how concentrated is a solution, how much solute is in the solvent. There are actually 4 ways of measuring this because apparently one wasn't good enough. So we have 4 ways of measuring it. The first 2 have to do with just straight percentages. Percent by mass is what's the weight of my solute, the mass of my solute in kilograms, and what's the mass of my whole solution in kilograms. Now it's important to remember the solution part because in a little bit we'll see mass of solvent and it's different. So mass of solution and mass of solute, what percentage of the whole solution is the dry part that I put in the liquid, right? That is percent mass. Percent by volume is similar. What's the volume of the solute? What's the volume of the whole solution? So if you've got a liquid and you're diluting the liquid and you're told to make it a 6% solution, then you take some volume that you have of the solute and you dilute it until you've got a lot more, right? And the stuff that you put in was only 6% of what's left. So it's a pretty straightforward division, right? Just percentage. The other 2 are a little bit more challenging. Molarity. This is actually the most common one that you'll use, especially in labs in our class. Molarity is how many moles of solute are in how many liters of solution. So this is easy to use in a chem lab because you use the molar mass to figure out how many moles you have of this thing, and then you put that stuff in the bottom of a beaker and you fill it up to 1 liter, and you've got however many moles in a liter, and you can figure out the molarity pretty simple. Molality is still moles of solute, but now we're not talking about how many liters of solution, but how many kilograms of solvent. So this is the one that gets confused with percent mass because it's kilograms, but it's kilograms of solvent, not kilograms of whole solution, okay? And it's the moles of the solute on the top, not the kilograms of solute on the top. So these are the 4 ways of measuring concentration. Let's do a little math together. So if you dissolved 5 grams of solute in enough solvent so that the entire solution had a mass of 1 kilogram, what's the percent comp by mass? 5 grams out of 1 kilogram. What percentage is 5 grams out of 1 kilogram? We have to be in kilograms on both sides, so I've got to convert my grams to kilograms. So 0.005 kilograms divided by 1 gram is 0.005%. 0.005, change that into percents. Now I'm at 0.5% composition by mass. Okay, pretty straightforward math. Similarly, if you dissolve 10 milliliters of solution of solute in enough solvent, so the entire solution had a volume of 4 liters, what's the percent comp by volume? Well, then I would say what percentage is 10 milliliters of 4 liters? That's pretty straightforward. Again, just got to convert to liters. So 0.01 liters, that's 10 mils, divided by 4 liters, that's 0.0025. I need to go to percentage, so 0.25% composition by volume. Okay, here's another one. If you dissolve 3 moles of solute in enough solvent to create 2 liters of solution, what's the molarity? Well, 3 moles, 2 liters, 3 divided by 2 is 1.5 molar. Okay, and the last one here, if you dissolve 6 moles of solute in 8 kilograms of solvent, what's the molality of that? 6 moles, 8 kilograms of solvent. I don't care what the whole solution weighs, just the solvent weight, right? So 6 divided by 8 is 0.75 molal. Now, sometimes I won't give you the units you need. Sometimes you have to convert. So let me show you one of those, okay? 5.0 grams of sodium chloride is dissolved in enough water to make 500 milliliters of solution. What's the molarity? Now, molarity, remember, is moles over liters. I didn't give you moles. We need to do a little bit of math to get moles. So 5 grams of sodium chloride, how many moles is that? We have to figure that out first. Sodium is 22.99 grams per mole. Chlorine is 35.45 grams per mole. Add them together, and we get 58.44 grams per mole. That's the molar mass. So I need to use my 5 grams and the 58.44 grams to figure out that I have, in fact, 0.085558 moles of solute. Way too many significant digits, but I won't correct it yet. Remember, we only correct at the end. So that's how many moles of solute I have. Now, moles of solute per liter, right? And I have 0.5000 liters. Do the division, and I get 0.171116 molar, but I need to correct for significant digits. So here I have 2 sig figs, here I have 3 sig figs. I need to go to 2 sig figs, 0.17 molar solution. Okay? If you have any questions, put them in the comments field below. Otherwise, I will see you tomorrow as we continue to march through this, and we'll make this work, okay? God bless you. Jesus loves you, and so do I. I'll see you tomorrow.